Hello everyone. Today is the 71st day of Leetcode 75 challenge. Let's begin with the 71st question. Question 1268 Search Suggestions System. The level of the problem is medium. I will request you to read the question beforehand as I will deep dive into the PPT and explain it in simpler way. Now let's understand the problem in the easiest way possible. So if you can see, you are required to design a system that suggests product based on a given search word. Okay. So to make this line easier, I will say it like if you go for an e-commerce site, okay, take it as that way, and you have a search bar here, okay, and you typed mo, okay, so all the most common items or all the important items as per the description given will be appear here. Like suppose from M what can come? A man's shoes, right? Uh, Mangoes, right? Whatever. But as soon as you write M A, this won't be there, right? There would be mangoes, then there would be uh, mattress, like something like that. So that is what is this, okay, basically. So you are given an array of strings called products and a string called search word, okay. For each character typed in search word, you need to return at most 3 product names from product that share the current prefix. The suggested products must be in lexicographically order, basically increasing order lexicographically. If more than 3 products match the prefix, only return the first 3 in lexicographical order. You need to output a list of lists where the ith list contains the suggested product after typing the first I character of search word. So to make this problem easier to understand, I hope you understood this e-commerce website example, right? So this is what exactly we have to do, but they here have put on constraints there that the most 3 products should be coming, right? So if you are searching for M, so lexicographically increasing products, for example, let's take the example, it's this one only, right? M, like M for if we can get mobile, right? Mobile, then mobile is smaller than money pot or money whatever, right? And money pot is smaller than monitor, right? We are taking this example. So if you can see, this is lexicographically increasing order because M O, then it's B, right? And we have here N, so B comes before N, right? Understood? So this is the thing, right? Lexicographically order means this is the thing, and also you can see that it's B, right? So it's coming before. Here it's N. Here also it is N, right? And after that we can see that it's I here, but MON EY, right? Money pot is MONEY, right? So E after B we have B, since it's B, right? So it will come before. That's the thing. Okay. So I hope you are getting some idea here. Let me get to the question again. Okay, coming to the point 3. For each character typed in search word, suppose the M you typed, you need to return at most 3 product name from products. So you will be given a products list. Okay, from there you have to take the 3 product names which share the common prefix. Suppose if we have some 3 products starting with M, so all those 3 products should appear here, and the way it will be coming out in the list, it should be in lexicographically order, basically increasing order, as we saw the example of money pot, and the other one, right? Mouse, what was it, was monitor. Okay, so if more than 3 products match the prefix, suppose if there are another 5 products or 2 products, right? If these 5 are matching, then only return the first 3 in the lexicographically order. Got the point? So basically at the end you just have to return the top 3 search result of the prefix typed in the search box, like we do in an e-commerce site. Okay, so I hope you got some idea here. So let's look at the constraints now. And also, yeah, you it's written here, you need to output the list of lists. So basically it means that if you typed M, okay, you got the 3 results, right? You store it in a list. Okay, this 3 L1. Again, then you typed MOU, so you got another 3 updated lexicographically increasing list. Okay, so you have added it in L2. Okay, and this becomes a 2D list. Basically you have to return this. Okay, result for M, result for MOU, and there could be result of MO, another list will be there. Okay, so I hope you understood this point number 6 now. Now the constraints of the problem is products array which is given to us, length will be from 1 to 1000, and products each value length would be from 1 to 3000. Okay, and sum of the product's length would not cross more than 2 into 10 to the power 4, and all the strings of the products are unique. Okay, so you won't get the common strings like you're getting 2 times apple, right? It will be apple, mango, banana, all will be unique. Products of I consist of lowercase English letters only, and search word length, since you're given product list and search word, right? So search word length could be from 1 to 1000, and search word consists of lowercase English letter. Okay, so I hope you got the idea of how the problem is proceeding and problem constraints. So let's move to the next slide now. Now let's understand the input output explanation. Okay, so let this is the products given to us. Okay, and suppose this is our keyboard or something like that, and this is a search space. Okay, so they have given us search word, right? Search word is mouse. So from mouse we will type first M. Okay, so lexicographically you will get three results when you type M. Okay, which are this: mobile, money pot, and monitor, like this. Mobile, um, money pot, and monitor, right? Great. Then you will store it here. After that you will go and write mo, right? Then what will happen? From here you can see that mobile is there, money pot will also be there, and monitor will also be there because it's matching, right? Because all of them starts with mo. Okay, and in lexicographically increasing order they are. After that you will be typing u for mouse, right? From mouse u, but here you can see that mobile will automatically get removed because the third character it is b. Money will also get removed, right? And the mouse pad will also get removed, right? Because they don't have u in that, in those. So what will happen? From our product list you can see that we have only mouse and mouse pad with us. So in increasing order we will get mouse and mouse pad. Okay, then again you will type, and this will be stored here. Okay, then you will type s, again this will get stored, same thing will come, right? Then again you will type e at the end, and you will get this, and this will get stored at the end. Okay, so I hope now you got that this is basically a dynamic searching. Okay, it is a dynamic searching kind of a thing in an e-commerce site, if you can just relate that. Okay, so let me give you a live example if you still have some doubt in it. Okay, so let's take the example by searching, suppose, something from a. Okay, so like look, you can see that we get Adidas shoes from an air fryer oven. Let's suppose these are the products, right? But now you want something which is let's suppose apple, like it starts with p. Okay, then you can see that previously this the here we are getting how many products? 6, 9, 10. So suppose these are 10 products will be stored in the list. Okay, and if you can see that these are also lexicographically increasing order. Then if you go for Adidas, suppose D, right? Then you can get here Adidas shoes for man, adult diaper, then sneakers, then whatever the thing is. Then if you can go for another D, right? Then it shows you Adidas slippers. This is the brands, right? So this list will keep on getting stored, right? As soon as you keep on typing it, right? So like if you take the M example, you will get something like this, right? This will get stored. Then this list will get stored. This list will get stored. So this is how the thing will keep on going, right? So I hope you understood this example from the live website to make it much more clear to you. Okay. Now let's go back to our PPT. Okay. So I hope you understood the input-output explanation. Now let's move to the next slide. To understand what problem is asking, we should build up an intuition to the problem. Let's start it by understanding the goal. So we are asked to design a system that suggests product names as a user types a search word, right? Each character type, we must return up to 3 lexicographically smallest products that start from the current prefix. Correct? We have to return 3, right? There is a limit set to us. If you can see the example previously, here also it was of 3 size, right? Now, a brute force solution would be for every prefix, scan all the products, filter the matches, sort them, right? Basically, suppose it's mouse, right? Given to us. What I will do, I have the product list. Okay, I will go. First of all, I will sort this. Okay, in lexicographically order, it will sort it automatically. Then what I will do, it will take some time. Okay, and this will take O of n, suppose. Okay, iterating this. So what will happen? I will take M. I will come here. I will take this word. I will check whether it's does it contain M or it does not contain M. Right. Suppose it, in a best case scenario, it might take O of 1, right? But in worst case, it might take O of n. For each word, let it be not O of n, let it be O of L. Okay. And so this will take a lot of time complexity, because you will come, you will take this word, you will iterate this word, you will check whether does it has mo or mou, whatever the prefix is. You will place it, then you will go for the next word, you will check that, you will go for the next word, you will check that, right? For each iteration you will be doing that, so it will take a lot of time complexity. It will be n log n, right? Then it will be added with n multiplied by the complete array length. Let suppose it be m multiplied by the complete length of the word L. Okay, something like this. Okay, it will take something this kind of time complexity. So it will be a very it will be too slow when product queries will be a too large one, right? So I hope you got this. So the time complexity will be nearly about n log n for sorting the product list, plus n. This is the size of the prefix given to us. Okay, multiplied by length of each word in the product, multiplied by the, as you will iterate the complete product list, right? M. Got it? Okay. So what could be the better approach? A better solution is we already discussed, right? However, the more efficient or better approach would be using a trie prefix tree, which naturally organizes words by prefix and avoids repeated searching and sorting. Okay. In my previous video, video number 17, there I have talked about what is a trie data structure and how a basic trie is set up and used in very depth. Okay, I have given you the code in class base so that you can use it everywhere. Now try is to recall, try basically helps in any problem related to string. Okay, where we have to search or whatever, something like that, like dynamic searching is there, counting is there, right? In that kind of scenarios, using prefix for larger queries, using try for larger queries makes it much more sensible and logical. Okay, so to understand, I will give you the complete knowledge here about the try, but if you watch the previous video, video number 17, this will give you the basic understanding and the basic template, how a template was coded for the try. Okay, this will help you a lot and save you a lot of time to understand what we're going to discuss in this video number 71. Okay, so let's move ahead. So let's visualize the process now. Okay, so before going through this visualize process, I will like you to understand how the try will be formed and how we're gonna intuitively make the solution to it. Okay, let's start here. Okay, so let's begin. So I have written here one of the example of this. Okay, and I will explain it to you. It's mobile, mouse, money pot, monitor, mouse pad. The same example which was given to us in the lead code. And one more thing, I will request you to please, if you can, uh, look or just watch the insert operation in try from my previous video. If you can just watch this section of the video, only this much, it will be very helpful. Okay, I will provide the link in the I button. So in try, what usually happens is that in basic template we have two things. One, a verb flag value. Okay, a flag value, and a list here, which is basically, which stores basically alphabets from 0 to 26, like from A to Z. Okay, which is called as, suppose you could call it as children list. Okay, fine. This is the basic structure of a try. Okay, I'm just recalling the values. If you have seen my previous video, these are for those to recall the same. So in this case, we have to insert this value, right? So now let's start. Okay, let's first understand this. Here I have taken the raw product list which is given to us. Then I have sorted it. So when you sort anything, okay, in Python or C++ on Java, any string values, it automatically gets sorted in the lexicographically increasing order. How to prove that? If you can see, starting characters all are M, 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 M. Then starting second character is O, money, money, O, 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 O. Then it's B, right? Then it's N. Then it's again N. We know that B comes before N, right? And U comes uh, before N, right? So if these are already in a lexicographically increasing order. I have sorted them to, because the question already asked us that we need the solution in the lexicographically manner. So reduce the computation. If you directly sort the given raw list, the product list in lexicographically increasing order, it will reduce our headache of each time iterating and checking whether it is lexicographically in sorter or not. So this sorting basically helps us to reduce the searching operations to check whether it is lexicographically increasing or decreasing. Okay, so I've removed the raw list from here. Okay, let's start. Now I will take m from here. Okay, and some there will be a root node, and we will create this, right? And this will have, as we know, f, because it is not the end of the word now, and we place m here, and new reference node will be created for this, right? This way. Okay, but with this, with this, since this is the since we are taking the base template of the try and we are modifying it. Now, previously I said that in a try, we usually had a flag value which stores false and true. True means this is the end of the word. False means it is still not the end of the word. And we used to store characters here, which is basically reference pointing to the other to its reference node, like here what we are doing, right? But here we will storing another thing, which is suggestion list. So it will become something like this: flag, okay, list for characters, list of suggestions, okay. And the size of this will be how much, if you can remember? Since we won't, it will be 3, but we won't be declaring any size here because we want to put everything what we get. Okay, so this will be our structure of the list. So what modification we did from the earlier template? We didn't do anything, we just added this suggestion list here. That's all. Okay, now why suggestion list, you will get to know now. Since if we have the suggestion list, okay, and having m here, right, because you are putting for m, right? Having m means what? You typed m's in your search box, right? And when you typed m, lexicographically increasing, what you will get? You will get mobile, right? You will get money pot, you will get monitor, you will get everything, right? Got it. So this will be basically placed in the suggestion list. Okay, now okay. Also one more thing, I know it's a lot to absorb. Please repeat the videos again and watch it for this. Okay, now this is done. Since a product list is given to us this way, right? So it's a very logical thing that you will be iterating the product list. Definitely will be iterating the product list, right? So the for first iteration you will get mobile, right? And let's take the example, you just have the mobile word with you in the product list now. Okay, just take this. Now when you are creating this try, for this m, you will get mobile because you only have mobile with you. Then if you store o here and its total prefix is mo, right? Then it will be again mobile because you have just mobile with you. Getting my point? Let me repeat again. This is a product list given to us, right? And it's of course or a genuine or obvious thing that you will be iterating this product list. So in the first iteration you got mobile, right? It's like uh, it in product, right? Something like that. So you from it is basically the mobile word first, right? You will send this it word into our insert operation. Got it? And that insert operation would be only having mobile with you, mobile with it, and this will create a try for the mobile. And for m prefix, there would be only one option with it, that is mobile, right? Now in the second iteration, suppose this mobile iteration is complete. Now the second iteration you will have money pot, right? Instead of mobile, now you will send only money pot above. Okay, so again it will start. Okay, it's m, right? It's m again. We already have m with us. So when it's m, and in its suggestion list, it only had mobile, right? But now it have money pot also. So the money pot will be added because this size or the size of the list, suggestion list, is not 3 till now. Then when mo is typed, again money pot will pop up because the product which is only shared above to make the try, it's only money pot, right? I hope you're getting this. So again in o you will be having mobile and money pot, and since suggestion list size is less than 3 or not equal to 3. Okay, so I hope you got this idea. Let me do the now let me do the operations. Great. So yeah, so we are iterating this, right? We have mobile with us now, right? Okay, and product also with us is mobile. Okay, you're doing the, just take it as you're doing the insert operation of mobile in try, right? Follow that. Just you have to do one more thing here. if the length of the suggestion, let me write it as SUG, okay, if it is less than 3, okay, so it will start from 0 1 2, right? So if the length of the suggestion is less than 3, please store the product which is shared above, or the name which is shared above. Just take it that way, okay. So we wrote M, we typed M here. As soon as we typed M here, for this mobile, we will come to this node, right? And we will check, is the length of the suggestion less than 3? Yeah, it is less than 3 for this node, right? For this M, keep that in mind, right? So here, what we will do, let me write it somewhere. Yeah, so I will write it here, okay. So here it will have mobile, okay. That means you had the mobile, you placed M here, a reference node will be created, right? And here, for this, it's pointing to this, right? When I will search for M, I will be getting mobile now. Got it? Great. Now we will come here, we will see it's O, right? So here, since we're standing here, we will place O. Me do it somewhere like this. I hope that should make sense. Now for O, a new reference node will be created, right? And we will be standing here. Now for O, we will check, does the suggestion list size is less than uh, 3? Yeah, it's 0 actually, because for this reference node we don't have any suggestions, right? For MO, so new suggestion lists will be created and mobile will be pushed here, okay, for this O. Fine. Now after O, it's B, right? So we'll place B here, and a new reference node will be created, and it will be false, and we will be standing here. And again, same scenario for B, MOB, for the prefix MOB, the suggestion for this particular reference node, it's empty, so mobile will be added here, okay. Now after B, it's I, right? For I, again a reference node will be created. Let it be this F, and this will be empty, and a new suggestion list will be created for this, for the same, right? Mobile, and it will have mobile with it, right? Now after I, it's L, right? For L, again a new reference node will be created, again false, and for the prefix MOBIL, we will be having this mobile in the suggestion list, okay. After L, we have E, right? Okay. For E, a new reference node will be created for sure, and this will become true. We know why. Please pause the previous video for that. This true basically depicts that this is the end of the word, and it will have a prefix, the word with the word mobile with it in the suggestion. Fine. So we can see that for mobile we have it. So this tree structure which is created, please mind my drawing here. This basically says that when you type M, so what it will do, it will come here, it will go to a reference node, and it will look, okay, for M we have only mobile right now. Then when we will type for MO, right, prefix of M, do we have O for it? Yeah, we will come here, okay, and the O reference is pointing to this, right? And for this we have mobile. Got it? Now let's take another example. It will be much more clear now. Now let's take mobile is done, right? Now we are looking for money pot. From the root we come, we will check, okay, we have the M. Great. So for M, we will coming to this reference node because it's true, right? And here, since we have shared only money pot with us, okay, we will be standing here and we will check the suggestion lists for this M. We say it's only size of 1, right? It's not 3. So what we will do, we will store money pot, okay, and it will be lexicographically sorted already, okay. After that, O is done. O is not, sorry. Now we will iterate and we will look, okay, it's O now. So for O, the reference node is this. Again the same scenario, money pot will come here because you don't have it, right? And the suggestion list ID is less than 3, and we don't have to put anything because why we don't have to put anything, because uh, O is already there. Now from O, now we will come to N, right? Now we will check, okay, in this reference, since we are standing here, we have only B, we don't have N with us. So what will happen, we will add N definitely, and for this N, a new suggestion list will be created, okay, because MON will not give you mobile, right? It won't give you mobile, it will give you money pot or monitor, right? So this was till mo, right? And this was for b, right? If you remember, for this reference. So this is completed. So what will happen? We will add n here. We will come to this reference node below. Okay. Here what will happen? A new box will be created like this: money pot. Okay, comma. So now what will happen? This For this, a new reference node will be created, right? This way, f, and it's empty now, and this will be pointing to this. Got it? B1 is pointing here, if you can see. And for this is the suggestion. Okay, let me write it again clearly. So I will draw the suggestion list here. Okay, it was mobile, right? Great. Now MON is done. Okay, and we are standing here in the orange box. Now for that, uh, it's E now, right? So what we will do? We will add E here, and a new reference node will be created. Okay, let me write it again nicely. Okay, fine. For this, a new reference node will be created. Let me draw it a little bit bigger, like this. From E, it will be something like this. Uh, F, and then it will be E is there, right? So for this, we will be having only money pot, right, with us in the suggestion box. Money pot. Great. Okay. Now I will stop here for this money pot. Let's take another example. Otherwise, it will be a bit longer video. The space is also less. Now let's take this one. If you can see here, we have monitor with us, right? M is matching, and we have passed only monitor for inserting, right? M is matching. So what will happen? We will have monitor here. You know how it will come, right? Now it's clear to you, I guess. Now we're standing at O, right? Now do we have O? Yeah, its reference is this one. And for this, we have mobile and money pot, and we will have monitor also. Okay, great. Now for after O, we have N, right? And we have N, and N is this orange part. And here we had only money pot, not mobile, because it's MON. So here we will have monitor with us. Got it? Nice. Then after this, we have I, right? So definitely a new reference node will be created here, I, and a new this reference will be created with F, which will be having a suggestion box with it as monitor. Okay. I hope now you're getting the intuition now. Now let's take another example because it will be a lot bigger otherwise. And also, I will request you that please draw this diagram along with me, so it is much more or much better understanding for you. Now we have the mouse, right? Its mouse M is matching, right? But it is already of size 3. Okay. Now what we will do? We will, since we know that this is lexicographically increasing, right? Mobile is smaller than money pot is smaller than monitor, right? And now we have mouse. So what we will do? We will take the last word of this, like from here we will take monitor, because we have to keep the smallest lexicographically order, right? So if we have to of course compare it with the last word. So we will check, is the monitor or the last word is greater than the mouse or the coming word? Like it will be -1, right? So no, it is not, because mouse is greater than monitor, because we have u here. If you can see here, we have u which is greater than n. Got it? So this will not get stored here. Okay. Then we will come to O. O is matching, right? We will come to his reference and suggestions. Again, the same scenario. We will see, okay, the suggestions list is 3 size already, and mouse. Mouse is lexicographically is greater than monitor also. So we cannot replace them. If mouse was smaller than monitor, what would have happened? Instead of monitor, we might have stored mouse there. Got it? After that, that's done, right? Now it's U. So we don't have U, right? So here U will be created. The new reference node will be created for this with F, and a new suggestion box will be created like this, which will be having mouse with it. Got it? Great. Now similarly, after that we will see, okay, we have U. We will place U is already there. Now we will look S will be placed here. I hope you're getting it. I know the diagram has been a little bit bad now, but yeah, let's bear with me. S, right? With S, a new reference node will be created with F, and a new suggestion will be created as mouse with it. Got it? Same thing. Now let's skip the mouse. Let's come to mouse pad. Again, coming back here. M is matching. Great. We will come to its suggestions. Already three size. Again, mouse pad is greater than monitor. We will check from the last word in the suggestions. Okay. Then we won't be doing anything. We will just move ahead. Again, we have O. Same scenario as mouse. Again, here we will see U, right? And for U, we will be coming here. Red. Please follow the red now. Now we will see here. Okay, U is there, and his reference is there, and suggestion. He's only having only one size, length of one size. So what will happen? Simple. We will add mouse pad here, right? After that, reference is already now that is done, right? Then we'll come down here. We will see S. Okay, for S the reference node is this. This was for U, right? Now S we have mouse again, and we have space, so we'll add mouse pad, right? And this way the tree will grow. Now the tree will be common after that, because after mouse, after E, a new reference will be created for pad. Okay, and there we will be only having mouse pad with us. Okay, and for the monitor also, after mon itor, for the itor part, we will be only having monitor word in that. Okay, because there is nothing as moni or monit in the given product list. So now if you search M, okay, if you type M, lexicographically increasing, you will get this three as the result. Okay, let me write here. Okay, then you will type O, prefix O. For prefix O, what we will get? M O. For O, what we have? We have mobile money pot and monitor. Got it. Then if you type N, suppose. Okay. Then for N, M O N, you are standing here. For N, what we have? We have money pot and only monitor. These two will be our result. Okay. And after that, you write I. So what will happen? You will come here. And for I, what we have? Here, we have only monitor. Only monitor will be displayed. Got the point? Now coming back again, instead of N and I, now suppose our list is M O U. Now what will happen? M O U, this red line, right? So M O U will return what? It will return mouse and mouse pad. Got it? So I hope you're getting the point now, right? So this is the what dynamic search will look like, and it will give the order as the question expected us to be. So I will request you to please uh, rewatch the intuition part, this complete diagram part, and also I will request you to watch the video 70 for the understanding of the base template of try, how insert, search, and starts with operation works. It will help you a lot. Also, please follow me by drawing the diagrams in your paper, so it will be much more clearer to you. Now let's move to the next slide. So, so this is what is written here in the visualization process. Okay, the same thing I have written here. Why only three? Problem asks max three, saves memory, avoids extra comparisons. Try is prefix top three. Typing M, note returns three words. Typing MO, go deeper, get narrowed to three. MOU, mouse and mouse pad, right? This is what we did. Try pre-computes, auto-completes, so lookups are instant. So if you go and do this with the brute force approach, it will take a lot of time complexity, right? Now, let's see how we can simulate this. I will give a high-level part here that we will have a node structure of children, suggestion is word end. Children to reference for the next characters, suggestions to keep the three logical, as we see we kept the three logically lexicographically increasing or the smallest word of the prefix, and is end to mark whether the word iteration is complete or not, right? If in the scenario, if you can see here, suppose this mobile was completed here, right? So I marked true. That's the same thing. So there will be operations, commonly insert operation, search operation, which will be get suggestions prefix, okay, and lexicographically guarantee. So this means while inserting, we always maintain sorted suggestions. Thus at query time, retrieval is instant and lexicographically correct. And search will what it will do, it will traverse each character and prefix. Basically, it is basically starts with M, starts with O. If you have watched my previous video, you can compare it with that. M starts with M, MO starts with MO, MOU starts with MOU. These are the prefix. Got it? Now the insert operation is as simple as that. We will just inserting the characters to make a tree. Okay. Now let's move to the next slide. Now what we figured out? We figured out that since the problem required checking prefixes and giving top results, we realized try is the best fit because it naturally supports prefix-based queries. We avoided using sorting plus binary search because while they work for exact matches, they become inefficient for dynamic prefix checks and repeated queries. You can also try coding the sorting plus binary approach, right? Let's see what we get. By storing only top three suggestions at each node, the try ensures quick access to results without extra sorting later. Okay, so I hope you understood the intuition explanation. Now let's move to the next slide. Now, since we got the intuition of the problem, let's look into the approach how we're gonna solve it. So let's start by the step one, which is defining the node class. What does that mean? That the node class is having children suggestion. Okay, and also is and with. Okay, so this will create a reference node having these three parameters in it. Okay, 1 2 3, and this helper functions within it. Okay, in this try we will be focusing only these three functions: contains key, check if the child exists, add to add the child basically for the insert operation, and get to move to the next child node. Okay, this is done because to organize words by prefix and store them in top three suggestions at each prefix. So this is the node creation. Okay, so if I do like uh, suppose node dot something node dot function, so from this current node we'll get the output. Okay, now at step 2 we're defining the try class. We create a try with a root node. So basically in the class try we'll create another class try. In that what we'll do, we will have root variable which will be creating a new node. Okay, we have to start from somewhere, right? The root is pointing to this node. If you remember, I was saying earlier the root will be pointing to some node and we will start from here. We will storing m and the new reference will be created. So this is the beginning step. Okay, this is how we will be doing it. Now at step 3 we'll start the root node. Current node equals to self root. Okay, current node means, suppose let's take this random example. Suppose this is a try, right? And it has another here and like this something. So current node means you're standing suppose in this node, right? And if you have to check the suggestions list, okay, you have to check for the character, does it exist or not, and if you have to check whether it is false or true, we have to know, right? So that is why the current node is used here. So it will be like current node dot get. So this will get the character of this node, right? Okay, now for each character in the word, this is the insert operation. In the insert operation, this is the insert operation completely, right? So in the insert operation we will be iterating. For each child if does not exist, we create a new reference node to it by using this function. Okay, then we move to the next node using the current dot. After doing this, right, we use current dot get, so that we can move to the next node. So it will go like current dot add. We have added the node and created a new reference node to it. Then what we will do, if you remember, if we used to create a node and put the value in it, instantly we used to create a new node, right? Reference node to this. So this is done by current dot get ch. So what we will do, we'll create this node, done. We'll call the get function passing this ch, will stand here, right? So that for the next iteration, we'll place the value here itself and we'll create this again. Okay, this is how it will go. And to maintain the top three suggestions and every node within the insert operation, we only keep 3 word at max. So this is the code for this. The length of the current node suggestion is less than 3. Please add it, okay, append it, and please sort it. Okay, why we are sorting it? The same reason. There might be a scenario that, like, if you remember, suppose A was there, B was there, and C was there, and when we were trying to add this letter, this character or word, we used to check from the last character whether this is bigger or this is bigger. If this is bigger, we will remove this and we will put D instead, right? Now, in the same scenario, suppose we have B, okay, and we got A, right, and its suggestion is empty right now. So we just cannot put A and move ahead, right? We have to sort it. So that it becomes A comma B. So that is what we are doing here. And else case, if the word, this is the word, this is the scenario. If the word is less than the node's last word, if it is smaller, We will just replace the word and we will sort it again. The same reason as ahead, we will sort it again and we will move ahead then. Now continuing the step 3 insert operation, at the end of the word we mark it as complete. Now the for loop is done, right? All the functions and if case is done. After coming out, we are standing at the last node having this as false. Suppose this is a character here, C pointing here, right? So this is the last word. So current node dot set, this will set it as true. Okay. Why this works? While inserting, we pre-compute autocomplete results. So later, when searching, each node already has its top 3 lexicographically smallest word ready. So lookup is instant. Got it? Now for the step 4, query operation, get the suggestion. So what the insert is doing, insert draw has had done the work of creating the complete data structure tree. Okay. Now the get suggestion will have the prefix or the search word which is given to us, right? Now this get suggestion function will have this word with us and we will look for the uh, results. So how this will work, basically the main function, before going to this, the main function which is given to us, the main function here, we will create a prefix string and we will do for ch in search word which is given to us, the word to be searched. Okay, prefix plus equals to the ch. Suppose if it is apple, apple, we will be having prefix as a. Okay, and this a will be passed to this suggestion function. Okay, so this suggestion function, it will create a new current node to the self root. We will have the root here. Now what will happen for ch in prefix, for each character in ch in the search word, this basically means, suppose if you have passed a right now, okay, suppose again it was after apple, right? App, so the prefix will become app. Got it? So we will pass this app here. We will iterate this app now. Suppose app will be iterated. Okay, then we will pass this each word here. If not, if node contains key, if that, if not, basically if it is true, that means that we don't have a, we will return the empty list, that hey man, we don't have anything which starts with a or anything which has app with it. Okay, we might have a scenario that we have aple as the apple, right? So it will result in empty list. Got it? This is same as the starts with function in our try. Else if we have it, what we will do, we will just move to the next node. Suppose if it is a box, p box, this is the references, again p box, l. Okay, so since we had the a, we will move ahead, we had the p, we will move ahead, we had the l, we will move ahead. Okay, and each time when we move ahead, we'll keep on moving ahead, and whenever this complete iteration, suppose this apple iteration is complete, or suppose let's take the example of mouse itself. If we remember, if we have typed mob, or let's suppose if we have typed m, let it be like this, m, right? Then it was suppose o, right? Then it was suppose b. So if we had given the only, we had prefix mo, right? For if you remember, for mo we had what? We had mobile, moneypot, and monitor, right? For this mo. So after this doing this complete, we will return this. Okay, and this result which we will be getting, we will append it into our result array. Got it? So each node already stores top 3 words, right? So if it is m, we have the top 3. If we have mo, we have the top three, right? So yeah. So this is the how the suggestion get suggestion function will be working. Now step 5, the base function setup. This is basically the main function which is given to us. First, we sort the product to ensure lexicographically smallest suggestion. Beforehand, product is sorted. Then we iterate in the products list to perform the insert operation. After completing that, as I said earlier, we will create a prefix, iterate each search word which is given to us. Suppose if we are given to us, mouse was given to us, right? So this will be added in the prefix and this will be passed here. Okay, and the result which we will be getting will be stored in the result array, and we will return result at the end. Okay, so I hope you understood the approach explanation. I know it was a lot, but I tried to give you the in-depth knowledge of it. So now let's move to the next slide. The code is the exact copy of the approach discussed. Let's understand it line by line. Okay, let's start with the base function here. This is the function, main function given to us, and this is the things we create a try. Okay, then we have the insert operation, then we have the search word operation, and we return the result. Coming back here to the node class. Okay, node class will have these three parameters: children's of 26 length, true, false. Initially, it will be false, right? Because we don't know whether the word is ended or not until and unless the iteration for the complete word is done. If you can see, we call here, right? And if you can see the set end function, it makes it true. We have functions so contains key to look whether we have the key or not. If we have it, good. Add to add the character in the try to get the character or the next reference node, and set end to set it as true when the word is at the last. Okay. Now here, this is the try. Now this try will create a root. This is the complete insert operation, and this is the complete get suggestion operation. Okay. So this is self-explanatory. I hope you're getting this. I already explained this part. So now let's understand the time and space complexity here. So here, n stands for number of words. Okay. L stands for max length of any word. M stands for length of the search word which is given to us. Okay. So why it's n cross n? L first before, because inserting all words in the try takes n cross L time complexity. Why? Because n is what? It's the number of words which we gonna insert in the try, and the length for each word will be L, right? That is why it is n cross L in the worst case scenario. Okay, that would be if we don't have any matching prefixes. Suppose we have monkey, then we have ball, right? So it will definitely take n cross L. But if it is monkey, then it's money, right? So it will take very much less time complexity. Okay, for inserting. Now, why from where m is coming? M is coming from the suggestions function. This one. This one is given n cross L, and this one is giving m. Why m? Because searching for each character typed m characters, we iterate for m. That means that the length of the search word is m, right? So we will iterate this complete word, right? That is why it's m. And space complexity is n cross L, because the number of, in the worst case scenario like this monkey and ball, the total space which will be required will be n cross L, right? So I hope you understood the time and space complexity also. Now let's move to the next slide. Now since we have the understanding of the code, let's look at the dry run of the example. Here I have taken the same example again, and I will try to give you a rough idea of the dry run, because doing the dry run will take a lot of time here now. Okay. Suppose let's start here. Okay. Where it is? This one. So this will help you inserting the word in the try. Okay. So this will basically call this insert function here till here. So how it will go? It will create a node. It will have false to it, right? This one. It will iterate the word which is mobile right now. And yeah, sorting and all that stuff is done already, right? So mobile comes first, then comes the money pot, then comes the monitor, then comes the mouse, then comes the mouse pad. So what will happen? We will check, does it contains in our no try, but the try is already empty, right? So it will return false from here. So what will happen? We will call the add function. This add function will be called, and basically we won't be putting here m. It will be a reference. So I will just write for our better understanding m here, and a new reference node will be created. You can see that a node is placed in this reference. Okay, with false, and after that we'll move to this node. How? We will call this again. We will come here, this, and what we will do? We will check. And one more thing, order of ch means we are getting the ASCII value of it. ASCII value of small 7 is 97, right? And if it is m, right, it's 109. So what will happen? We will subtract 109 from 97, and it will give me 12, right? So in our 26 size list of children, in 12th index, this m will be stored. Basically, the reference of its reference of this index will be stored, right? So what will happen when we do the get function? When we pass it here, we take out the value here, and it's 12, right? So this will be returned, and we will be standing here. Got it? And after that, what we will do, we'll check the length of the suggestions, which will be also placed somewhere here. Okay, it's if it is less than 3 for this current node, which is of course right now it is empty. So what will happen, we will append the word. What is the word? It's mobile, right? So we will append mobile here, and we will sort it again. Okay, sorting will be done. And after this complete tree is created, I will request you to follow my intuition from before and draw this tree. So what will happen next, again mo will be there, then again the suggestion list will be created again, b will be there, right? This like but at the end when it's mobile e, right? So here the f will be converted to true by calling set end function, this one. Okay, now this will create the complete tree. We have the idea now. And this get suggestion, after the country creation is done, we will iterate the complete search word given to us, which is mouse in this case, and this prefix will be sent here. And what we will do, we will go to the current node, we will stand here, we'll come and stand here. And what we will do, we will for ch in prefix, we will iterate that prefix. Suppose we have mo with us in prefix, so from m we will call this contains key function, which will come here. Again it will do the check, and in the try we will check, do we have m? Yeah, we have the m, so it will return true. And we will just, if it is m, if it is mou, right? So we will go to its next node by using the get function. Again it's u o, from then we'll come to u, right? Now when this iteration is done, we will return the current node suggestion. So if you remember in mou here, if you remember mou, we had mouse and mousepad with us, right? So this will be returned. Okay, so I'm letting this dry run to yourself. It is same as uh, the structure which we draw of the try from scratch is the same exact copy here. Okay, so I will request you to do the dry run by yourself and try to understand how the try is working with suggestions here. And if we have any doubts or confusion about the solution we arrived at and how we arrived at it, I would suggest going back and understanding the intuition, the approach and the code, and also the try concept from the video 70. And after that, do a dry run by yourself on 2 3 examples, and I'm pretty sure you will understand both the solution and the thought process behind it. Now let's move to the next slide. Now, since you're familiar with the problem and the solution, let's move to the lead code and code the solution. Let's start by first defining the node class. Class node. We'll create a definition of init, basically a constructor. This will be having what? Self dot children equals to none, because it will be empty initially of 26 size. We will have self dot suggestion empty, self dot is word, and as false initially. Okay, now we'll have another function def. This will be contains key self ch. This will return true false whether we have the key or not, or the character or not. Suppose do we have the a or not, which we are looking for. Children, or this will convert, then this will be subtracted from is not none. Okay, def, it will be def add self ch. Okay, this will be adding the character in the try. So it will be like self dot children, yeah, children ord of ch. Let me see here also, it was a syntax error. You can see, okay, ch minus order of a and equals to node. Okay, again there will be another function get self dot ch. Okay, this is all the same, just we won't be having this here, and we will just return from here. Okay, def, it will be set end self and it will be self dot is word and equals to true. Okay, now let's code the try class. Try. This will also have the init function with it. It will go like self dot root equals to node. Okay, def insert function self comma word which will be of string type, and it will return, its return type is none. Okay, it is not mandatory to write, but for our understanding we are doing this. Current node equals to self dot root for ch in word. If not, me copy this, paste it, dot contains key ch. We will do what? If it does not contain, what we will do? We'll just add it, right? Add ch with the new node passed to it. Okay. After that, current node will move to current node dot get loop character. Okay. Then the insertion of the character is done. After that, it's time for the suggestion. If length of the current node dot suggestion suggs suggestions, if it is less than 3, please in current node dot suggestion, or you could just copy this here and yeah, suggestions, check the last word. No, if it is less than that, current node dot suggestions dot append the complete word. Okay, in current node dot suggestion will sort it. Else, if the word which is less than the current node dot suggestions last word, in current node dot suggestions last word will be replaced by this word, and again we will sort the suggestion list. Okay, and after that, current node will have this set and function call. Okay, now let's code this get suggestions function self dot prefix we will be having, which will be of string type, and return type is what? It's list, right, of string type. So here current node will have the root again, self dot root, and for ch in prefix, if not in a current node contains the key, if it does not contains, please just return the empty list. Otherwise, if it has, it's this, just do what, just go to the current node get, just go to the next character, right? Then at the end just return, if obviously we will be having something, right, we will just return current node just suggestions from here, and that's pretty much for the function here. Okay, now let's code here also. We will have try. We'll call the class here. Okay, object is created. Then for word in sorted products. Okay, this will sort the products list if you remember initially. Then we'll call the insert function from the try, passing this word one by one. Okay, and after that we will create a result array and prefix string for ch in search word given to us. Prefix will be having chn result will be appending the output try. We will call the try dot get suggestion, passing prefix to it. Okay, and after that we will just return the result array. Let's try by submitting for the sample test cases. So the sample test cases has passed. Now let's finally submit the solution. So we have successfully submitted our solution. Now the code of the problem is available in my GitHub repository. You can find the link in the description. Thank you everyone.